Hi everyone, welcome to this new lecture of a new session of CT111. So, for the interest of time, we'll just get started right away. Um, we were talking yesterday about the minimum Hamming distance decoder, and all that it is basically it's kind of implementing this principle of distance minimization that we have already seen in the context of Bayesian maximum likelihood receiver. So here the distance minimization is in terms of Hamming distances. And the way it works is, in case if suppose you can imagine a channel decoder, which can kind of store in its memory the type of Hamming spheres that we were drawing yesterday, right? Then what that decoder will do is, whenever it gets an n-bit received sequence, it will see which of these green dots it is closest to, and it will decode that particular green dot as the most likely transmitted code word. Okay, so that is the basic idea. Now, in reality, when the small n and the small k become very large, then it becomes difficult, almost impractical to implement this minimum distance decoder. And so there are some smart ideas which kind of bypass the need of explicitly doing this minimization of Hamming distances, but that we'll cover later on. For the time being, let us assume that this type of minimum distance decoding is implemented at the receiver, and that receiver actually has the algorithm which can measure the distance of any received binary sequence with all of the 2 to the power k possible transmitted code words, and then it will select the one which is the closest. Okay. Today we are going to start off by observing one interesting implication of this this minimum distance decoding, and in general this type of arrangement where the transmitted code words are intentionally spaced as far as apart from each other, meaning that their minimum Hamming distance, that dh min, that parameter dh min that we had defined last time, is as big as possible. You would have seen in this diagram that I intentionally made dh min, which is about 7 bits here, to be pretty large. I mean, I could have drawn the same black and green circles, but instead of drawing them in this nice manner, maybe I could have put a green dot right here. And in that case, dh min would have been just 1 bit, and that would have kind of, as we will see, it would have defeated the purpose of channel coding. Today, what we are going to start off by is looking at two different metrics. So one we will call as the error detection capability of the channel code, and the other we will call as error correction capability, detection versus correction. And in order to do this in a kind of to be able to do this for different values of dh min, we won't be doing this entire Hamming sphere diagram all the time. So we'll take instead a shortcut, and what we'll do is we'll just consider a two-dimensional version of it, where I'm going to just draw a straight line. But what you will need to remember is that this straight line that I will be drawing is always for two code words that are closest to each other, meaning that I am looking at the dh min, the minimum Hamming distance. The other thing that you have to keep in mind is that although I'm drawing just this straight line, in reality, it is this entire cloud that you have to think of. Cloud or the universal set, where there are a lot of black circles which are not the valid code words, and then there are these green circles which are the valid code words, right? So you have to kind of go back and forth. Okay, so that is what we are going to do. Now, one more thing that I want to mention is that suppose the transmitter has sent this particular code word, this particular green circle. No, it's an n-bit binary sequence. And suppose that the binary symmetric channel introduces exactly the 7 bits of errors so that this green circle turns into this green circle at the receiver, right? If the symmetric channel introduces just 1 bit of circle, 1 bit of error, then you will be receiving any one of this black dots at 1 bit radius. If it introduces 2 bits of errors, then you can be receiving any one of these dots in the second hemisphere and so on. But if it introduces 7 bits of errors, and those two exactly in the right spots, then it could be that you transmitted this green circle, but you end up receiving this green dot. Okay. Now, in that case, this minimum Hamming distance decoder will have no way to know that errors have happened. It will just think that this was the transmitted code word here, and it will be happily decoding that code word. But if less than 7 bits of errors happen, then there is no way that this green circle can turn into this green circle or this one or this one, right? Because they all are 7 bits apart. So if 6 bits of errors are introduced by the channel, or 5 bits, or 3 bits, or 1 bit, then you are guaranteed that the receiver will see only the black circle, only the invalid code word. It will never see a green dot. Is that fine with you?
Sir, 7-bit for any values of n or some specific values of n?
No, I'm just talking about this particular example. I'm showing you. Right here, how can this transmitted code word turn into this transmitted code word? Because only if you get 7 bits of errors, 1 bit, 2nd bit, 3rd bit, 4th, 5th, 6th, and 7th. So only for this particular example, I'm saying that if you have less than 7 bits of errors, maybe 5 bits or 6 bits or 3 bits, then you are guaranteed to land on top of a black circle, which is an invalid code.
N is equal to 3 for this example, right?
No, we didn't define what the n is.
Okay.
So what I'm trying to get at is that the minimum Hamming distance decoder will always be able to detect an error if the number of bits that are flipped by the BSC are less than 7. And the other thing that I want to to mention is that if the number of bits that are in error are less than or equal to 3, then this minimum Hamming distance decoder will always be able to correct those 3 bits of errors. Because as long as this number of bits in error are less than 3, the received code word is ensured to be among this Hamming sphere. And this is the transmitted code word. And so the minimum Hamming distance decoder will always decode correctly. Does this make sense?
Yes,
Yes.
sir.
Yeah.
Okay, so I mean, these are some new concepts. So if you are not fully confident that you have understood what I'm talking about, it's okay. You just bear with me. As we go along and we look at some examples, hopefully things will become little clearer. Okay.
Hello, sir.
So let us move on. Yes, Pujan.
Yes, sir. For greater than 3 bits Hamming distance, then it will always give error.
Exactly. You are pointing out exactly the correct thing. So as long as the number of bits in error is less than 3, then you are guaranteed that that particular example, the decoder, the minimum Hamming distance decoder, will be able to correct all those errors. If it is more than 3, then you are sure that it will make an error.
Yes.
Okay, so we are going to define 2 different metrics. One is what we are going to call TD. The other is TC. Okay. So what is TD? It is exactly what I said. It is the maximum number of bits that can be flipped by the BSC, beyond which the detector may not be able to identify that the errors have happened. Sometimes it may still be able to identify, but there is not a guarantee. The reason why it is not able to identify is because when more than TD bits are in error, particular transmitted code word can actually turn into some other code word. And in that case, the minimum distance decoder will think that that is the transmitted code word. It doesn't know that the errors are happening. And this TC is the error correction capability. This is defined as the maximum number of bits that can be flipped, at or below which the minimum distance decoder is guaranteed to decode correctly. Okay. And these are both functions of the minimum Hamming distance for this particular channel. Okay, so now, as I said, we'll draw the simpler 2-dimensional versions of diagrams for different value of minimum Hamming distance. And remember that as we go through these examples, you have to understand that these are for different coding scheme. One coding scheme will have only one value of DHmin. When we change DHmin, it means there is some other different coding scheme that somebody would have designed. Okay, so that is what we are going to do now. So
Hello,
very
sir.
first, yeah.
Sir, in previous example, TD error correction is a 3 bit, and for error detection, you said that bit flipped cannot be greater than 7, right?
Right.
But sir, if 9 bits or 10 bits are flipped, then also we can detect error that error happened.
Yeah, you are right. I'm saying that what is the maximum number of bits that can be flipped, above which the detector may not be able to identify. So as soon as you reach 7, that is when you say this is TD. You are right. If 8 bits are in error, then again the detector is always going to be able to identify. but 8 is already above 7. So you stop at 7 and you say that TD is 6.
Sorry, sir. What you said last?
See, the definition is that TD is equal to the maximum number of bits that can be flipped by the channel beyond which the detector may not be able to identify that BSC has introduced the errors. So in that example, as soon as you reach 7 bits that are flipped, you run into a case when a green circle turns into another green circle, and now the the decoder is not able to identify that errors have happened. So that defines TD. TD is this kind of the minimum case. Yeah, if you go above 7, then again at 8 bits, you will always be able to identify that the errors have happened. But we stop at the very first time that we are not able to identify.
And sir, if 7 bits are flipped, then also we cannot say that the green dot is detected. Right?
Correct. So that's why I said may not be able to. I didn't say that always will not be able to. When 7 bits are in error, sometimes it may be able to identify that errors have happened because you end up on a black circle. Exactly like what you are saying. But sometimes it will be a green circle that you land on top of it, and then the detector will not be able to say that errors have happened.
Okay, sir. Thank you.
Okay, so let us consider first a simplest case where minimum Hamming distance is only 1 bit, which means that there are 2 valid code words which are sitting next to each other. With only 1 bit of error, this code word can turn into this other code. Remember, these are our visualization diagrams, right? This can be some n-bit code word. This will be another n-bit code word. We are not specifying what n is. All that we are saying is that the minimum Hamming distance is 1 bit. So now in this case, if 1 bit is an error, and if this code word can turn into another code word, obviously the detection capability is 0 bit, right? Because even if 1 bit is in error, you can't detect anything. And if 1 bit is in error, this minimum Hamming distance decoder cannot correct it either. So even TC is 0 bit. And this is typically kind of either a very bad design of channel code, or maybe there is no channel coding at all. So what is the next thing? This is the case when BH_min has become 2 bits. So no matter which pair of code words you pick, which 2 code words you pick, you will at least see that they are different in 2 bits. So now you can see that if only 1 bit is in error, then no matter which code word is transmitted, you are guaranteed to land on top of this black circle, the invalid code word. And so this minimum Hamming distance decoder will say that this is not one of the valid code words, so the error has happened. So it is able to detect 1 bit of error. So TD is 1 bit. Can I say TD is 2 bits? Well, no, because if 2 bits are in error, this can happen. You can land on top of a valid code word, and now the Hamming distance decoder is not going to be able to say that errors have happened. So TD is only 1 bit. Okay, what about TC? So I have drawn this Hamming sphere around this code word and this code word. And for the sake of simplicity, I didn't draw the full Hamming sphere, but I just drew the decision boundary, the outermost part of the Hamming sphere, just this portion of it. Now we will notice that because the minimum Hamming distance is 2 bits, the Hamming sphere around each code word can be at the most 1 bit. And those Hamming spheres will touch each other as what I have seen, what I have shown. And so now, if the receiver says this particular code word, it is confused. It doesn't know whether to go here or here because both are equidistant. And so it will not be able to even correct this particular case. PC is 0 bit. What if DH-min becomes 3 bits? Well, first of all, we can say that TD has to be 2 bits because up to 2 bits can be in error and you are guaranteed to be on top of a top of a black dot. And also interestingly now TC can be 1 bit of error because if only 1 bit is in error, no matter which code word is transmitted, you are guaranteed to be within the Hamming sphere of that particular code word. And the radius of that Hamming sphere is exactly 1 bit. And so we can say that if 1 bit is in error, for this particular case where DH-min is 3 bits, the minimum Hamming distance decoder is always going to be able to correct that 1 bit of error. Okay, what if DH-min is 4 bits? Well, the diagram looks like this. TD goes up to 3 bits, right? 1, 3. But unfortunately, I cannot increase TC to be 2 bits because if I do TC of 2 bits, then I have to draw 2 Hamming spheres which are touching each other like this. But that is a problem because now if I land up on this particular black dot, the minimum Hamming distance decoder doesn't know whether to go here or there. So at the most, again, this detector can be correct only 1 bit of error. If 2 bits are in error, it gets confused because there are 2 code words which are both at 2 bits of distance from this particular code word. What if the minimum Hamming distance becomes 5 bits? Well, now I can say that TC is 2 bits because my Hamming spheres, I can draw them to be of radius 2 bits and they are not touching each other because DH-min is 5 bits. So with 5 bits, TC becomes 2 and TD becomes 4. And so on. If minimum Hamming distance is 6 bits, TD becomes 5 bits, but TC still remains 2 bits. However, if it becomes minimum Hamming distance becomes 7 bits, then now TC also increases by 1 bit. It becomes 3 bits. TD always keeps on marching. It becomes 6 bits. Okay. So this is kind of a visualization of the powerfulness of the channel coding scheme. Powerfulness here is defined in terms of TC and TD. Obviously, the bigger these numbers are, the better it is. The channel code becomes more and more powerful. And what we have seen is that in order to make channel code more and more powerful, we have to somehow increase the minimum Hamming distance. The powerfulness of channel code, as measured in terms of TD and TC, is entirely the function of DH-min. Who can tell me if I want to write the formula for TD in terms of DH-min, what will it be?
DH-min minus
DH-min minus 1.
Exactly, it will be DH-min minus 1. Okay, how about TC? TC is a little more complicated.
Greatest integer function
DH-min
of
minus
Integer division of TD by 2.
Floor function of
Greatest
DH minimum by
greatest
3.
integer
Function of TD by 2.
of
Very,
DH
very
minus
good,
1
very
by
good. I think you got it exactly right. It is floor function of TD by 2, which is to say that it's a floor function of DH-min minus 1 divided by 2. So that is what I have written over here. Okay, very good. Okay, so that is one topic that I wanted to cover. Now let us move on to another topic. And now we are going to start talking about. Yes, we are.
Sir, sir, it is also following the pattern of floor function of DH minimum by 3. So is it a correct here?
DH-min divided by 3.
Yes, sir.
No, if I
Floor
take
function of DH minimum floor function
Yeah.
of DH minimum
no,
divided by 3.
it is that is a wrong formula, because if I take this example,
8 bits
Five-
won't happen.
Okay,
5 divided
yes,
by
sir, yes, sir. Okay, yes, sir, sorry.
Okay, so now let us go to another topic. And here I'm going to ask you to start thinking of how to kind of design these channel coding schemes. Okay. So, we drew this block diagram of channel coding where there is a box, which is, we called it channel encoder. The input is K information bits and the output is N encoded bits. So what we are going to now start is to think of the input bits as forming a vector and the output bit as forming another vector. Okay, so this will be kind of an application of the algebra that you have studied in your high school. So the input bit, we are going to denote it as a vector M, and it is always going to be a K cross 1 vector. I put this transpose sign here, this T sign. All that it says is that although this vector is written as a horizontal vector, actually it's a tall vector, not a horizontal vector. It's not a 1 cross K vector, but you take this 1 cross K and transpose it. You make the row turn into a column, and so you get a K cross 1 vector. I mean, I could have avoided this transpose notation and just written this vector like this, the tall vector. And then I wouldn't need to do this transposition. But this is a little more cumbersome. It takes more space. So it's just purely for practical reason that I'm using this transpose sign. Don't get confused by it. But always think of this M vector as this K cross 1 vector. It's a tall vector, not a flat vector. And similarly, the output of the channel encoder is again going to be an n cross 1 vector of encoded bits. And we are going to convert M to C by doing a matrix operation that we are going to define on the next slide. Now, a few things that I want you to keep in mind. This M is always going to be zeros and ones. Okay, we are always going to be talking about bits. The output is also going to be zeros and ones. Right? So we are always going to be talking about binary code words at the output of channel. And in this matrix product, the elements of the matrices are also going to be binary. So everything is going to be zeros and ones in our algebra formula. What you will notice is that even when the input is zeros and ones and the elements of the matrix are also binary, the output can still be non-binary. But we are going to assume that it is turned into binary by taking modulo 2 operation. So we are always going to do modulo 2 on the output of this matrix product. It doesn't have to be that. In some advanced channel coding techniques, the input may be not binary, the output may be not binary, the matrix itself may be not binary, but we are not going to, that is not part of the syllabus. This is what you have to keep in mind, that everything is binary and the output is always going to be taken modulo 2. We will not say that output is turned into binary by modulo 2 all the time, but that is what you have to assume. Okay, so the way that we are going to turn the input vector M, which is a k-bit vector, into an output vector C, an n-bit vector, is by multiplying M with what is known as generator matrix. And its size has to be n cross k. That is the only way that you can turn k cross 1 vector into n cross 1. Okay. So this is the output of the channel encoder. This is the input to the channel encoder. And this one here, G, is the encoding operation itself. Okay. There's another matrix which is also very important. And I'm just going to define it right now. Okay, don't worry about what it is, where it came from, how that is the case and all that. Just take it as a definition. And as we move along, it will become clear to you what this matrix is. So this matrix is called parity check matrix, and we are going to call it as H. And most of the time, this G is used at the transmitter encoder. H is going to be used at the decoder, at the receiver. And this H is sort of a unique matrix which works on, by the way, this n cross 1 vector. Okay, because the receiver doesn't see k cross 1. It always sees n cross 1. So it works on this n cross 1 vector, and therefore its size is some u cross n. So the H can indeed be multiplied with this n cross 1. But the unique thing about H is that if you multiply H with any one of these C vectors, any one of the valid code words, any one of the C can be any one of two to the power k valid code words So no matter which code word out of 2 to the power k you pick, so a kind of a surprising thing about H is that if you multiply that C with H, you are always going to get all 0 vectors. This output is going to be always all zeros. Meaning that if this part is any one of those green circles, then you are going to get zeros. But if C is not a green circle, if C is a black dot, then this will not be 0. There will be some ones in this output of H times that black dot. And that is the crucial property of H which will allow us decoding. Again, everything is modulo 2. Okay, so when we say we get all zeros, it's only after doing modulo 2 that we get all zeros. And then what is U? U is the difference between N and K. It is the number of redundant bits, sometimes also called the parity bits, that the encoder introduces. Okay, so these are some definitions. It will become clear to you as we move along. Okay, so when we take some concrete examples, you will understand what I'm talking about. And so the first concrete example that I'm going to take is the repetition code. This is our first scheme that we are going to study, but we have already studied this, so I'm going to very quickly flip over the slides. The encoding scheme, you take only one bit at a time at the input, so small k is 1. And we just repeat it n minus times, and then we transmit the resultant n bit long code word, and so the rate is 1 over. This diagram, I think you have probably seen earlier. Suppose if you are transmitting some 6 bits, then the encoder turns them into 18 bits like this. And then maybe some of those 18 bits get flipped by the BSC. And then we said that a good decoding strategy would be to do majority voting. And so therefore we decode this particular sequence. So this is the rate 1 over 3 repetition code. Okay, so this we have already seen earlier, so I won't spend much time on this, but let me now write the G and the H matrices for, just to make it a little spicy. I'm going to ask you its rate 1 over 5 repetition code. So how can I write G matrix? Okay, so in order for you to be able to answer this, let me say that the way those matrix products look like will be like this. So I should do it in a different color, maybe line thicker. Okay, so first of all, what is going to be our M vector?
One and zero.
Yeah,
1,
but what is the size of M vector?
1 cross 1.
1 plus 1. It's going to be just a scalar, meaning that we are just going to have only one information bit at a time. So it's going to be just a scalar. I'll still call it a vector by putting rectangular brackets around it, but it's, it's just a scalar. Okay, now let's not put G as of now, but let us see what will be the C vector. I'll write C vector here. So C is, because of its rate 1, 5, C is obviously going to be 5 bits. C0, C1, C2, C3, and C4. But what are the C0 to C1 to C4 for this repetition code?
Zeros and ones.
Zeros and ones I know, but in terms of the message bit, M0, this M0 can be
M0
0 and
repeated.
1.
M node, M0.
So all of them are going to be M0. So I will write it here M0, M0, M0. So now I will ask you what algebra I have to do to turn this M0 into 5 M0s. That is going to be my G matrix.
Five cross one unity
Sir,
matrix.
5.1 with all elements 1.
Very true. Vandan and Harsh gave the right answer. So only way I can do that is I put 5 ones as a tall vector. 5 cross 1. And this works out mathematically because this is 1 cross 1, this is 5 cross 1. So I can multiply them and I get 5 cross 1 as the output. And because all of them are ones, at the output I get all of them to be M0s. So this is going to be the G matrix. Now, H matrix is little complicated, but we'll see what happens there also. Remember, this H gets multiplied by C, and the C vector is now going to be, in this case, the same bit, M0, 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 and M0. And over here, what I want is a vector with 4 zeros. Why 4? Because this vector is always has a length of the number of redundant bits that we are adding. In this case, we added 4 redundant bits. So this is always 4 cross 1 vector. This is always n cross 1. In this case, 5 cross 1. So what H matrix can I put over here so that I get 4 cross 1? First of all, what should be the size of this H matrix?
4 cross 5.
4 cross 5. Yes. So this is H. Now, can somebody tell me how to write H so that H times this M0 vector turns into 4 zeros?
All are 0.
Yes, all are 0.
No, that is trivial. I don't want to do trivial operation.
1 minus 1, 1 minus 1.
Remember, this is all going to be binary, right? As soon as you say minus 1, you are not in binary world.
All are 1.
Only way you can populate this H matrix is by ones and zeros. Minus 1 is not binary.
So all can be 1.
All cannot be 1. Okay, I'll say one for first row of H. Okay, in the first row, suppose if I put 1, 1, and the rest of 3 to be zeros, then am I going to get 0 here at the first output?
Yes.
Yes,
Yes.
yes, sir. Modulo
Because
operation.
XOR of the same bit with itself is obviously going to be 0. This is what we are doing. We are doing XOR operation in this matrix product. When we turn the product into modulo 2, it's same as XOR. So that is my first thing, for first row. My second row can be what? I'll start with 1 and then
For 1
One
and 0.
even number of ones.
0, 1, 0, 0. So now I'm comparing the first bit with the third bit. Because first and the third also have to be the same. And then first and the fourth also have to be same. And then finally, first and the fifth also have to be the same.
Sir, I had a doubt.
Yes.
Sir, in the previous slide, you told that H matrix needs to be a unique matrix.
Yeah.
But if we have 4 ones and zeros and then permutation of them, then also we'll get a zeros.
Okay. So when I say unique matrix, that uniqueness is for all different channel coding schemes. Maybe, yeah, for this particular repetition code, you can come up with some different edge. But what I meant to say is that it's one unique matrix for which this operation of H times M is always going to give you all zeros. Okay, so don't be fixated on that word unique, but keep this equation in the mind. Okay.
Okay, sir.
So what we observed is that for the repetition code, G is a vector of all ones, and that I'm going to write it like this. And H, you will see is like this. It's the first column is all ones. And the rest of it is identity matrix. Make sense? First column is all ones, and then the rest is identity. Whereas G is just a column vector of all ones. Right? You see identity matrix here?
Yes, sir.
Yes,
Okay.
sir.
So this is how we can say that no matter what the value of n is, H is always going to be of this form. All ones will be the first column, and the rest is going to be identity matrix. And G is going to be always all ones. So that is how G and H are defined for repetition.
Hello, sir.
Okay, so yeah.
Sir, I have a doubt that why the result of H multiplication of H and C comes out to be U cross 1.
Because H is 4 cross 5, this is 5 cross 1, so obviously this is 4 cross 1.
Yeah. No, so my question is why U we have to choose?
Okay, so that I will answer just in a moment. Just bear with me. Or maybe let me give you kind of a preview to the answer. What is U? U is the number of redundant bits that the encoder is introducing. And what you will notice is that for each added redundant bit, that redundant bit is going to be added in not only the repetition code, but in all the other channel coding schemes that we will see. The way we add that redundant bit is by having this type of constraint. See, for the repetition code, this second redundant bit is added with a constraint that its modulo 2 operation with the first bit has to be 0. The third bit is added also under the same constraint. And the fourth bit is also added under the same constraint. What is the equation for the constraint by which each of these redundant bits are introduced? Well, that equation is exactly specified by the corresponding row of H matrix. And because we are adding U redundant bits, H will have U rows. Does that answer your question?
Yes, sir.
If not,
And
maybe if you are not very clear, just bear with me. As we go through several examples, it will become clearer.
yes, sir. And sir, the G matrix is all ones and H matrix is ones and identity matrix. It is applicable only for case of repetition, right?
Only for the repetition code, correct. So that
Okay.
is what we are now going to look at another scheme that we have not seen so far. This is a new scheme, and you will see that G and H will change. So before we start on this, I'll take a very quick break. Okay.
Hello, sir.
Yes.
Sir, I have a doubt that in the previous scheme, why C all are M not because we depend on the majority. We take majority case, so all M there should be means why all M not C not C1 C2 C3 C4 should all M not.
Because I am saying that this H matrix gives all zero vector as the output only when it is multiplied by a valid code word. If you multiply it with any received sequence, then it will not be all zeros. Only when you multiply with a valid code word, which is this code word here, all of them are M zeros, then you get all zeros. That is the definition of H matrix. So here we are not talking about we are not talking about majority voting. We are not even talking about decoding right now. We are just defining H matrix. And the H matrix is defined such that when you multiply it by this M, I don't know why I wrote it as M. It is, yes, in this case, it's vector of all M zeros, but in general, this has to be C, vector C. So whenever you multiply H with C, you get all zeros.
Okay, sir,
And
I
that is,
got it.
okay, fine. So now let us consider this single parity check code. It is also extremely simple coding method, but also very, very powerful in some sense. In its own, it is very weak. Okay, if you just have only single parity check, then it's probably one of the weakest channel coding. But the good thing about SPC is that you can almost think of it as an atom. And as atoms kind of combine, you start getting more and more complicated schemes. So in subsequent schemes that we will be looking at, it will be basically some clever combination of the SPCs. But right now we are just going to consider only the atom, only one SPC. So what is this one SPC code? What does it do? Well, very simple. All that it does is it takes n-1 bits at a time at the input, and it just adds one extra bit, the nth bit. And this is the reason why we have used the term parity check bit. So this extra bit, the redundant bit that is added, is just the parity check. Parity meaning whether all of them have, say, even number of ones. If that is the case, then this added bit is going to be 0. And when this even parity is not met, it will turn into 1. And then we append that nth bit at the end of n-1 information bits, and we get n bit long code word. So a specific example is that you get m1 to mn-1. And then you add this parity check bit as just summation of mk mod 2. Okay, so this is a very, very simple code. Obviously, the rate is n-1 divided by n. So you will see that it's in some sense counterpart of the repetition code. For repetition code, as n becomes larger, the rate becomes closer to 0, 1 over n. Whereas in this case, the rate becomes closer to 1 as n becomes larger. Basically, what it means is that as you make n to be larger and larger, this added parity check bit is not going to give you much protection at all. It is as if you didn't do any channel coding. In that sense, it is the other end of the spectrum compared to the repetition. Now, this is kind of a visualization of what this SPC code is. Keep this diagram in mind because we will be using this type of diagrams later on. By the way, this is called also bipartite graph. Bipartite. So what this bipartite graph is? Well, it has two types of nodes. One is in circles and the other one is in the squares. And the circles are never connected with each other. The squares are also never connected with each other. The circles only connect to squares, as it is shown here. Okay, so what does this diagram say? That this is a single parity check code with rate 3 over 4. So we take 3 information bits, M1, M2, M3, or M0, M1, M2. And then we add the 4th bit, which is this parity check bit. And that parity check bit is added in a way that if I take summation of all of these 4 bits, and that summation is indicated by this S1, this is guaranteed to be 0. Why is that the case? Because remember, this parity bit I am adding such that if there is odd number of ones here, then I make it to be 1. If it is even number of ones here, I make it to be 0. And so therefore, if I add all of these 4 bits together, which is what this graph shows, this 4 bits are going to this sum bit, and when I sum it up, I get 0. And that is where this parity check name comes. If you take this SPC code word and if you do this parity check, it is always going to be satisfied. You are always going to get, which means that you are always going to get even number of ones. And that becomes your transmitted code word. First 3 code word bits are same as the message bits. The 4th is the parity bit. Okay. So how to decode this SPC? So we take the n bit long code word, and then we compute the modulo 2 sum. Meaning that we send these 4 bits up to this square node of the graph. And then we just sum them up. If the sum is 0, then what it means is that maybe none of the bits are in error. Or it could also be that some even number of bits got flipped. Then also the sum will be 0. However, if it is non-zero, then you know for sure that the errors have happened. Either 1 or 3 or 5 or 7 bits have been flipped. So all that this S bit over here can tell you is whether the errors have happened or they have not happened. And also it will be able to tell you that errors have not happened only if one bit has been flipped. If only one bit is flipped, suppose M1 is flipped or M3 is flipped or this P1 is flipped, and the other bits came through fine, then S1 will be not 0. And then you will say that some bit has flipped. But if 2 bits got flipped, maybe C2 and C4, they both got flipped, then again S1 will be 0. And now you will think that no bits are in error, whereas in fact 2 bits are in error. And so therefore, I would say TD is equal to only 1 bit. To get more than 1 bit in error, you can't say for sure. The other thing is that because this is a pretty weak code, TC is 0. Although you can say that 1 bit is flipped, you don't know which one of these 4 bits got flipped. Because all that it does is it just adds these 4 bits up together and looks at the sum. If the sum is 0, it says that, okay, maybe no bits are in error. Or maybe 2 bits or 4 bits are in error. That is all it can say. If sum is 1, then it says, okay, something bad has happened. I don't know whether 1 bit or 3 or 5 or 7 bits are in error. But, and I also can't tell you which bit is in error, because this is all that I do. Okay. So what are the G and the H matrices for this rate 4/5 SPC code? Okay, first of all, this time I'm going to write H matrix. I want to say that H times C is 0s. Now, C is for rate 4/5. C is going to be basically M0, M1, M2, M3, and the 5th bit, parity bit, is going to be just sum of all them. So M0 plus M1 plus M2 plus M3. So this is my 5x1 C vector. Now, how many redundant bits I have introduced? Only 1. And so this is going to be just a scalar. Remember, it's a U cross 1, but U is just 1. So this is going to be just a scalar, 1 cross 1. This is 5 cross 1. So right away, you can tell me that the size of H has to be what?
Cross 5.
1 cross 5.
1
1
cross 5.
cross
1 cross
1
5.
cross 1 cross 5. Now all you have to tell me is how to fill up this one.
All
All
1
are
or
1. All 1.
All ones, exactly. 1, 2, 3, 4, 5. What are all these all ones? Well, they are just this edges of this bipartite graph. The edge means there is a the edge means that there is a 1 there. Definitely, you probably want to mute your mic. Okay, so this is going to be the H matrix. for H vector for the parity check. Now, let's look at the G matrix. So remember G, the input to the G matrix is going to be just the message vector, which is M0, M1, M2, and M3. So this is a 4x1 vector. And oh, sorry, I want to multiply it with some G matrix. So that what I get is the encoded vector, which is M0, M1, M2, M3, and this last one has to be M0 plus M1 plus M2 plus M3. So it's a 5x1 vector. So first of all, what should be the size of G?
5 cross 4, sir.
5 cross 4.
5 cross
5
4.
cross 4. And who can say what G actually will be?
First four
Last
row
row
are
with all one
and last one are all
and
one.
with 1 0 zeros.
So first will be identity.
At bottom, all ones.
All ones.
And then here it will be all ones. So does this remind you of something?
Sir, in repetition, all ones are before identity matrix.
Yeah, I mean, I can put all ones even before identity matrix in this case. I would just put this parity bit first. But I think what you observed is correct, that this G matrix for SPC looks a lot like H matrix for the repetition code. And the H matrix for the SPC what was the G matrix for repetition code?
All ones.
Here H is all ones. It's almost as if G and H kind of got interchanged. H for the SPC is like same as G for the repetition, except maybe you have to flip it, you have to transpose it. And G for the SPC is a lot like H for the repetition. So that is what I have written here, that for the SPC port, H is always going to be vector of all ones. Whereas the generator matrix is defined as, sorry, so I think I made a mistake. This all ones is at the bottom. Okay, a silly mistake I made. So you will notice that all one vector is a horizontal vector that I have to put at the bottom. So G matrix looks like this. And the G and H for the SPC and the repetition are kind of very closely related. Okay, so we are going to end today's lecture here, but I want to have one half-an-hour session. Maybe either today or tomorrow. Because the reason is that there is one more channel coding scheme, which is, or there are two more channel coding scheme. One is called product codes. It's very nice scheme that I want to go over with you. And then the other scheme is what is known as Hamming codes. So we'll probably take 15 minutes to go over product code, another 15 minutes to go over the Hamming codes. So that is what I want to cover with you either today or tomorrow. The reason is that the next lab will be on the product codes and the Hamming codes. So I want to wrap up this topic of practical channel coding techniques this week. We have to cover two more schemes, product and Hamming. And for that, I will set up just a half an hour session. Let us see, is today from 12:30 to 1 is good for you?
Yes, sir.
Okay, so this is the announcement. From 12:30 to 1 today, we will meet again on WebEx, and we will wrap up this topic of practical channel coding. So I'll see you at 12:30 today.